When you're considering how to treat a historic bridge, I think you really need to start with what is the goal? What are you trying to accomplish? You have to start with, does it need more lanes for capacity to increase that opportunity value? Does it need a seismic retrofit in order to provide that security because it's an emergency route? Does it need more pedestrian facilities because it's providing connection? You have to consider those things, but you also have to consider the value of it in its current, like what it looks like and what it means to the community, because that's part of your goal. Can you maintain that feeling in doing all those other things? And sometimes if you have to do all those other things, they just become so overwhelming that by the time you'd finished, you would have lost that feeling. And if you've lost that, then were you doing the right thing?
The Van Buren Bridge, unfortunately, is made up of non-redundant steel tension members in some of those web diagonals, as well as the bottom chords. That design makes this bridge type a lot less resilient. Couple that with the west span, which has tension eye bars in that bottom chord, and together these make the Van Buren Bridge particularly vulnerable. If any one of these members were to fail, the entire truss span would more than likely collapse.
Trying to match that today, working on a historical side, like you start to lose, you can't recognize the bridge as an historical bridge in the same way it was. And ODOT really took the effort to say, what would it take to take this bridge to make it seismically stable? Now, that also brings in the question of how much life do you get out of a bridge of this age to begin with. So the challenge too, I think this was recognized by us, and I think largely recognized by the public and the community that we're working with, was that to make this thing continue as a vehicular bridge is really a fool's errand, because it would take so much work, and then you'd be only maintaining one lane.
The last time they tried to open it was in the early 1970s. So it's a swing span. The Coast Guard was saying, you need to be able to open this bridge on request within, and I think at that time it was a month. Okay, we're gonna test it out. They jacked up the ends, they started twisting it, and it immediately started to sag. And they ended up having to get a crane out to lift the ends back up to torque it back into place. And at that point, they took out the original bearings and fixed it in place and negotiated with the Coast Guard.
ODOT has a preservation crew because of the loss of Alsea Bay Bridge back in 1991. We did a bunch of research and discovered this cathodic protection scheme that uses electrical currents to reverse the corrosion in a reinforced concrete bridge, like Alsea Bay was. They found the technology and started dabbling in it, but it wasn't in time to save that bridge. But at the same time, they also started projects like Cape Creek Bridge down just north of Florence, and actually executed that one perfectly, and that started basically the saving of all the other coastal bridges other than Alsea Bay, all of the ones that were designed by Condé McCullough that, they're big and they're expensive and they're valuable both for historic purposes and also just for people to use and to get around. And so, we may spend $30 million doing the cathodic protection on one of those big bridges, but replacement might be $1.5 billion. The purpose of that crew is sort of twofold. It's the historic mission, but it's also just economics.
The Department of Transportation Act of 1966, which is essentially set up the DOTs, that act included a Section 4F. This was both signed on October 15th of 1966, where they recognized at the time there was a lot of hubris going on with the transportation agencies that were sort of blowing through downtowns of across the United States, and they weren't really considering effects to downtowns, and they're sending interstates through cities. And so there was this pushback at the time to really look at what are we doing as a transportation agency to the historic fabric of our country, and what can we do to change that? So these famous laws in Overton Park and Breckenridge in Texas led to these laws, which really, I think, have done a great service for us to really do a hard check about what are we doing and can we do something differently here. So in this case, of course, this is an historic bridge. That effort back in 2007 was really, hey, how do we make the bridge, as sound as possible for the possible future? At the time, there was a really willing partnership, I would say, between the city and DOT to look at opportunities for this bridge to possibly become a future, like pedestrian bridge. And so a lot of that effort was looked back and said, what do we talk about then? What do we do then? A lot of that community was still in town and has participated in the current process. But we as an agency said, okay, what alternatives do we have? So we actually looked at things like taking the bridge to the north, the Harrison Bridge, and making that the seismically stable bridge.
So one of the biggest deterioration mechanisms we see all over the state, but especially on Van Buren, is corrosion. Corrosion is a process that's going to eat away at the steel over time. It's inevitable. We provide paint to protect as best we can, but in the crevices between the plates, there's not much you can do about keeping the corrosion out. The other mechanism on Van Buren is the timber deck. Timber exposed is going to always start to rot. And the only real way to treat those are with these very toxic chemicals that kill the things in the river as well. And today we would not be willing to put those over our rivers. And so keeping up a timber deck is hugely costly.
So in the case of Van Buren, the biggest determinant was the load ratings. And so, for instance, in 2007, when we painted the bridge, it didn't look too bad. And so preserving it was a good decision. Then the load rating procedures evolved and got more stringent and looked at more details. But for instance, the timber deck on this bridge. And as a result, it went from looking pretty good to looking poor. My opinion, my impression, though, the inability to get around the metal fatigue issue and the non-redundancy is the thing that really took us to a place where we couldn't do something.
The cost of rehabilitating versus replacing can vary hugely. And it really gets back to that same question of what is it that you're trying to achieve? And you're still going to have to build a completely new substructure for the bridge because the existing substructure is sitting on soup, effectively. It's on toothpicks and soup. And so you're having to build that entire same substructure. And if that's a big portion of the cost, doing that cost comparison is never going to work out great.
It's going to require the construction of 2 temporary structures. One of the temporary structures that facilitates the existing traffic, and then we've also constructed a 730-foot long by 40-foot wide work bridge, which is directly behind us, which that facilitates removal of the existing bridge, including the trusses, the foundations, but it also facilitates construction of the new bridge substructure and superstructure. So it basically gives us laydown area, access for our cranes, all of our equipment, and that would include the demolition aspect of it as well. The benefit of a 2-crane approach, number one, it allows us to use company-owned equipment. The first step in this process is to lighten the trusses up as much as possible, and that's removing all of the existing asphalt concrete and removing the timber decking, which you can hear the guys with the chainsaws right now, which is what they're working on. Once we get the trusses, we call it skeletonized to their basic components, we'll prepare our cranes, we'll rig the trusses with some pretty heavy rigging. We determine and engineer what our pick points are, and we'll physically attach our cranes to each end of the truss and pick it, hoist it, and then turn and set it down on top of our work bridge. And in calculating the weight of this truss, and we've had, I think there's 4 or 5 different individuals that have gone through and physically calculated the weight of each and every component of the truss, and allows us to size our cranes. All of our cranes have certain capacity and a certain boom length, a certain turn radius, and so we have to design our work trestle or our work bridge to get within the pick radius of our crane. And then Staten comes in with their equipment. They shear all the steel components into smaller pieces that can be loaded into a truck and then hauled off. So in the olden days, and I've been around in the industry long enough to remember when you could actually put charges on the ends of the truss, blow it up, drop it into the river, and then you just yard the thing out with a bulldozer or a winch cat, something like that. But permitting agencies don't like that. There's also windows in which we can be working, and that's predicated by migratory fish restrictions. And our in-water work window on this project is effectively June 1st to October 31st. So while we're outside of the window, we're doing as much of the removal as we possibly can without impeding the Willamette River. So we're staying out of the river. We've got containment in to contain any debris that might come off the structure as we're removing it. It's dangerous work. There's critical picks, extremely heavy lifts, because once we've got that truss picked and up in the air, we don't have the option necessarily to set it back down.
We actually opened up a scrapyard at our facility, so we will be taking all of this steel and recycling it. The biggest challenge is getting it, on the trestle so we can process it. And we essentially want to process it down to manageable sizes to be able to truck it. So, we'll have shears processing it down to 20-foot sections and process it down even further.
So the timber was, I believe, governing the load rating, and the next most critical member was bending in the floor beam that supports those. That certainly is about cost benefit, and in the case of Van Buren, one of the tricky things was it's a pin-connected truss, in which a pin-connected truss has some serious vulnerabilities in terms of redundancy. That was okay in 1913. It's not okay today on the state highway system. And once we started thinking about that, the expense just went pretty crazy. So historic preservation is important, but taking care of the economic needs of communities is also important. Both contribute to the well-being of our communities.